This video focuses on the golden ratio, golden rectangles, practical ways in constructing them, and it covers number patterns and sequences, ratios, spirals, similar triangles, properties of a regular pentagon, quadratic equations, and connections between mathematics, art, architecture, and science.
Well, hello everybody. Today we're going to be talking about golden mathematics, the golden ratio in math, science and art. I'm Tony Bearden. I started AIMSEC about 20 years ago, and I've been working with teaching children and training teachers for a very long time now. Over to you, Caroline.
Hello, my name's Caroline Ainsley. I'm the founder of Bubbly Maths, and I'm a big supporter of Tony and her work. My mission in life is that every child on earth love learning and enjoy mathematics. And what better way to make that happen than to work with Tony to help teachers and find more engaging activities and resources. Sam.
Thank you. Hello, everyone. I am Samuel Okoth Ogalo. I am a teacher from Kenya who supports students and other teachers to implement playful learning as well as use of games, and also to be able to access digitally international mindful resources that are useful for teaching and learning. And I am very honored to join the two founders, Tony and Caroline, as we unravel the golden ratio in mathematics, science, and art. Thank you and welcome.
Well, the program today is going to be the golden ratio, as I've just said, and it'll help you to improve your own skills and understanding, but all these activities are designed for children in the classroom, and some for primary school, some for secondary. And you'll be looking at number patterns and sequences, ratios, at spirals, at geometric constructions, at similar triangles and congruent triangles, properties of a regular pentagon and quadratic equations, and connections between mathematics, art, architecture, and science. And as usual, we're thinking of learning as if it was on a spiral where we return to ideas that we've met in the past and keep in school, keep going back to the ideas, but each time adding more richness to the knowledge and understanding. So we build up that knowledge by revisiting the same ideas again and again. And that's signified in the spiral there. And in this session, the numbers 1 up to 12 start at the bottom because we're climbing this spiral. We imagine climbing this spiral, starting with an activity that very young children can do, anybody can do, and going right through to more demanding activities which you would do in upper secondary. So Sam?
Hello, thank you. Now we invite you to wear two hats. Now during these sessions, we invite you to wear both the hat of a teacher and the hat of a learner. As you do these activities, at one particular stage, we would want you to be able to think about it as if you were a student, as if you were learning, and also to be able to put on the hat of a teacher as if you are now trying to introduce this to your learners and achieve your learning goals. Welcome.
We're going to start with a very simple activity that anybody of any age can do, and it is something you can do with your younger learners. We're simply going to make a pentagon by tying a knot in a strip of paper. I've created a strip of paper, and all I'm going to do is I've just taken it out of an A4 sheet of paper, and I'm going to fold it just like you would tie a knot in your shoelace. And as you pull it, you have to just straighten out, keep those edges so that that part, as you pull it tighter, remains the same width as the paper. So for younger learners, you'd have to give them a bit of help, but it's a little bit magical, because if you pull it enough and then you flatten it a bit and pull it a bit and flatten it a bit, making sure that you don't make the strips bend at all, just end up with a flat 2D shape. Now, if you fold over these two, the external edges, the edges you no longer need, you have a pentagon. Now I'm going to cut those off, and perhaps Tony, you would like, because the question here is, can you see the pentagon? Cut those edges off. Can you see the pentagon with the pointed star behind inside? Can you see it? Well, if you do it yourself and you look carefully, you got to get it really close to it, you can get an idea of it, but you can see it if you have a nice, if you look up towards, oh, you can see it there a little bit. You can see it a little bit pointed there and a point here, and you can't see those, but you can see a point here. If I hold it there, you can see it a bit more.
Got
And
a very
look at that.
bright light behind it. You can just see the star. And that star is called a pentagram. And the pentagram's got lots of ratios in it. You see them in the diagram on the right. And all of those ratios, as marked, A over B, B over C, and C over D, they all have the same value. If you were to measure it, we're not going to do that this time, but if you measure it, try it yourself, measure it, and you'll be surprised. It is a beautiful shape with so many lovely properties, and this day is all about the golden ratio, and it's just a bit more than 1.6, I think you'll find, if you do those measurements. So the pentagram has been a symbol that people have recognized as having it's a lovely shape with a lot of properties that people have known about for a long time and incorporated it. You see, it's in the European flag on the left there. It's in the American flag on the right. And the building that's just called the Pentagon there in Washington, got an aerial view of that. You can see that's a Pentagon. We'll come back to the Pentagon several times in this talk.
And I've drawn the shape of the pentagon, that the outline you can see on there.
Well, that's lovely, Caroline.
Sam.
Now, as we move deeper into the golden ratio, after looking at the pentagon, now let us look at the golden rectangle. Have a closer look at the side that has been painted with the blue, and then the other side that has been painted with a light yellow color. Now, if we have a close look, you realize that if we split a rectangle into a square and another smaller rectangle, and then we go ahead, if we look at the ratio of the longer side of the bigger rectangle and the ratio of the longer side of the smaller rectangle, and then against the ratio of the shorter side, then we come up with a ratio, a golden rectangle having a property whereby, let us say that the longer side of the bigger rectangle is x, and the longer side of the smaller rectangle is 1. So this ratio of x over 1 that we get by dividing this further leads us to what is called a golden ratio. This golden ratio is solved by the equation of x over 1 in this case to be equal to 1 over x minus 1. Now, to be able to come out with this or bring out this property better, we get it by dividing a rectangle into a square and another rectangle, and then the inner rectangle also we divide further into another square and another rectangle, and then we can just do this measure and then try to find the ratio. So the ratio of the longer side and that of the shorter side will always be the same. And this process of continuously splitting the rectangle into a smaller rectangle and a square, a smaller rectangle and a square has been observed through various studies. And we are going to look at it further as we continue. So as we continue to delve deeper into the golden ratio, we are going to uncover more.
And the first thing we're going to do is sheep talk. So we're going to be doing some buying, and we're going to start with the letter A. Now, every time you have the letter A, the next step, it's going to be a B. And whenever you have the letter B, the next step is going to be AB. So we'll start with A. The next step, it's B. And then the next step, you have just a B, so B becomes AB, and the fourth step, the A becomes B, and the B becomes BAB. So you've got A, B, AB, and BAB, hence the sheep talk. So I'd like to pause the video and go ahead and do a couple, let's say 3 more steps in that sequence. So here we have, hopefully you've got that, and if you didn't, go back and just look at it carefully because it does work. And what we'd like you to do now is continue the sequence, keep going, but you can start with those 7, you can continue it on to 11 or 12, and create a table. When you fill in the table, so just make yourself that or just draw out that table, fill in the number of A's and the number of B's and the number of total number of letters at every stage. So for the first stage, it's A, it should just be 1A, and the total number of letters is A. Second one is B, and the total number of letters is going to be B. And then the next one, you've got A and B, total number of letters is 2. And then do that, continue that. So pause the video and fill in that table. And hopefully you've come up with a table that looks like this. So what you're looking for here is you're looking to, you can see the sequence in each row. And Tony, apart from the sequence, apart from the pattern, we're looking to spot something which we have been talking about already. But even if you don't know, are familiar with it, perhaps you can see how each number is being formed. What have you got to say about it, Tony?
Well, isn't it strange that when you look at these sequences, they're not all in lockstep with each other, but at the bottom numbers are 1, 1, 2, 3, 5, 8, 13, 21, 34. Those numbers are going to crop up again as we look at other activities. You may know what they are, but we would suggest that if your learners do this activity, they won't know, but they might spot. Isn't it odd that when we look at the number of A's, you've got to get to the third one here before you start with 1, 1, 2, 3, 5. and 1 and 0 come before. And for the number of B's, you've got 1, 1, 2, 3, 5, 8, and so on. So you've got the same sequences there. And we're going to learn much more about these sequences and how they relate to the golden ratio as we do this. So that's our sheep talk. And your learners, you can do this in primary school. It's very simple. And it's quite a good idea for them to do it in groups, and so they can check each other as they fill in the table. And perhaps, some of the group will do one count the A's, and then others in the group will count the B's, so they don't all have to do everything. That's our sheep talk. Now the next activity is lovely, and Caroline's going to demonstrate this to you, but just before I hand over to her and she spotlights this, you'll see the picture of the elephant. Now this is also, we're drawing it as a spiral, and Caroline's going to show you how what's the rectangle, which is divided into a square and a rectangle, which Sam talked about earlier, is shown again here, and the curve which goes round and round, going closer and closer in on itself, is a spiral. Caroline, and it starts right here with the 1, 1, and Caroline's going to show it. So I'm going to stop sharing so that Caroline can show you how she's going to do the elephant dreaming construction.
But to start this construction, you do not start on the bottom down here. You start, let's say 10 squares in, across and up. If you do that, you'll be 2, 4, 6, 8. Let's start there. We're going to start with a square. I'm going to just freehand that first square. And then this particular pattern, you just do another square. From here on in, we're going to match. So that's a square of a 1 by 1 square. That's a 1 by 1 square. We're going to make another square, but we're going to make it match there. So we're going to make a 2 by 2 square, because it's going to be the same width as the 1 by 1. Now I've got a 2 by 2. The next one, we're going to go in a spiral loop. So the next one we're going to do to the right. So we started there, we're going to keep going round that way. So the next one is going to be 1, 2, 3. It's going to match that. So it's going to be a 3 by 3. We're going to keep going this way. So the next one's going to be 2 plus 3, 5, 2, 4, 5. If I've got that right. And the next one, this is where you can see that you don't want to start right on the corner. So the next one's 3 plus 5. So it's going to be 8 long. 8 by 8. They've got that right. 2, 4, 6, 8. 2, 4, 6, 8. Yes. And so on. This one's going to be 13. 2, 4, 2, 4, 6, 8, 10, 12, 13. Across, somehow it gets easier as it gets bigger, as long as you get that first count correct. And then we're going to go across 13 plus 8, 21. And you've got to count 21 across. 18, 20, 21. Hopefully I've got that right. And that should be also, yes, 13 plus 8, 21. It somehow doesn't quite look like a square when you make it, because you'll make it into a rectangle. So on its own, it doesn't look like a square. And you can then continue on down here. The next one would be 34. Now talk about the spiral, Tony, while I draw it.
Well, in each of these squares, Caroline's going to draw a quarter circle with the center of that quarter circle at the corner of the square. And as you see it, it's another quarter circle, and now another quarter circle.
And this is a good exercise to help young learners get used to using a compass. It's an incentive for them to use a compass if they make each quarter circle, and then it'd be really accurate quarter circles. Then I'm just hand free drawing these.
And this isn't an exact spiral, but it's a very good approximation to it. And you can see there a suggestion of this elephant's head. And so what we have done is to say, what we suggest is that you get the learners to do this. You hope you'll like to do it yourself, and then have a bit of artistic license. And right, and you can see the elephant's head here. And what we've done there is not put the spiral, not start the spiral with the 1 and 1. So this gives him the end of his trunk here, and to turn the quarter circle that we had in the construction into a semicircle to give the elephant's ear. Put a little black dot in for his eye, and there's your elephant. So that's a really fun activity there.
I always see a parrot as well.
Yes, well, couldn't you? You could make other animals too.
Make the eye where the 21, and then you've got a parrot. You could get everyone to see if they see something different. And get everyone to make different size squares and then put them all together with different colors. Do lots of things.
Over to you, Sam.
Now, the numbers that we found out from the sheep talk have turned into a very beautiful drawing that we can now put a dot and closely looks like an elephant. But now, what can we do further with these numbers? Now, if we closely look at the numbers as we were drawing the spiral, we went from 1 to 2 up to 34. But it's just because of the space, but we could still continue. But how about now if we were using a spreadsheet to be able to find out something that might be common here? Now, if we try closely to look at the ratio of the consecutive terms and we put them as decimals and try to work out from the first term, which is 1, the second term, which will be 2 divided by 1, the third term, which will be 3 divided by 2, fourth term, which will be 5 divided by 3, fifth term, which will be 8 divided by 5, and we continue up to the 20th term, this ratio is going to bring out something interesting. Now you can try this out by yourself and notice a pattern come out. What do you notice? And do you see it converge somewhere? If we try to put it as decimal, up to at least the 20th term, we put it in 7 significant figures, we are going to get a term 1.6188034 as it is shown on the right hand side. Now, this term, does it have a name? This figure, does it have a name? Now, this is what is called golden ratio.
Now, what we haven't mentioned is the rule for finding the next term in the sequence. And this sequence is called the Fibonacci sequence. We're going to hear a bit more about the man, Fibonacci himself. But he introduced this sequence to the world. And if you add 1 and 1, you get 2. And then if you add the next 2 terms, 1 and 2, you get 3. And if you add 3 and 5, you get 8. And if you add 5 and 8, you get 13. And Caroline demonstrated that when she showed us the construction of the elephant, or the spiral that gave the elephant dreaming. And that's the formula that I used in making the spreadsheet, which you've got just 2 columns there. And so you can see that the spreadsheet's generated by adding the Fibonacci numbers to get the next number in the sequence, and by dividing each term by the term before it, as Sam explained there. And we've got our golden ratio, which is 1.618 approximately. We'll find the exact value later. Sam, do you want to continue and talk about that?
Sorry. Now, if we continue looking at this, our value, the golden ratio, 1.618, you will notice that just as Tony has explained, by just adding 2 successive terms in the sequence, it gives the next term, and this continues up to a term that we can call an nth term. Now, if we refer to this term as f of n, by the formula given below, we can be able to realize that the first 2 terms, that is f0 and f1, is equal to 1. And so to be able to find the nth term, which is f of n, it will be f of n minus 1 plus f of n minus 2, as it continues over and over. An addition of 2 successive terms as we go to the next term and the next and next.
So we're going to show you some pictures now that show how the golden ratio, we've got it all. If we keep our eyes open, we'll see it all around us. Caroline, you're going to talk about this one.
You can see here, if you look at the number of petals on the flowers on the top row, the lily has 1, euphorbia has 2, trillium has 3, columbine has 5. And then the daisy, I haven't counted them, but it's very likely to be a Fibonacci number, one of the numbers in the Fibonacci sequence. And not only that, in the center where the stamens are of the flower like a daisy, you'll see they have a similar pattern. You look down at the pine cone, the stamens of the sunflower, and we will be doing, you'll be seeing how this pattern can be generated by a GeoGebra as well. The nautilus shell has the Fibonacci spiral, and the way trees grow, you notice it starts with the trunk, and then you have 2 branches, and as it goes up, the trees tend to grow with the Fibonacci sequence in terms of number of branches.
Isn't it marvelous? And then if you look, and we'll say some more about this later, this picture of the Last Supper with the pentagon. Caroline made a pentagon with a strip of paper earlier. There's all good reason for that. You'll see that that's very much using the golden ratio again and again. And this is a picture from the air of the Great Pyramid of Giza, and the proportions in that pyramid, we'll say a little bit more about it later, are then also in the golden ratio. And the nautilus shell there is a spiral. As the creature grows, it needs more space, and it moves out on that spiral and blocks off the inner part and builds it so that he can always swim with the shell that way up. Sam?
Yes, now this amazing ratio also is shown in different architectural buildings, flowers. You can look at the US flag, but I will particularly talk about the Parthenon's layout. If you closely have a look at the dimensions, it has a foundation measuring 69.5 meters and 30.9 meters. And this creates a rectangle with a ratio of roughly 2.25 to 1. Now, this was meticulously planned to reflect the golden ratio. How marvelous.
The geodesic domes use the pentagons and triangles. So the pentagons built out of triangles. The way that the panels are put together, the length of each edge is really important, but as you'll see a little bit later, the ratio within the pentagons is really important, and it uses the golden ratio. And the great thing about them, you're using the golden ratio to create a structure using triangles, pentagons, and hexagons, and they're really energy efficient. The light reflects, stays in the dome longer, and it maximizes the volume within the construction, within the structure, which keeps heating costs low. It makes it a very energy efficient structure. And it's built with the golden ratio as part of the structure.
It's all related to that buckyball there.
Yes,
And now if you look at
Buckminster Fullerene.
Yes. So if you look at the sketch there of the pyramid, the Great Pyramid of Giza, you see that with the edge length 2, the line there that goes from the vertex to the midpoint of the base is gives you the 1.618. The golden ratio. Isn't that marvelous? And the height of the pyramid is the square root of phi, phi being the Greek letter, which you've seen written earlier as a circle with a line through it. That's PHI, phi. And man fears time, yet time fears the pyramid is an Arab proverb. And it's an amazing structure. It consists of 2 million blocks of stone, weighing in total 6 million tons. And its dimensions, 230 meters by 230 meters and height 146 meters, is bigger than any of the great cathedrals. For example, it's bigger than Milan Cathedral, which actually holds 40,000 people. I mean, it's amazing, amazing building. And I've put pictures in there of 5 of the beautiful cathedrals in Europe, and it's bigger than all of those. Very, this absolutely amazing pyramid.
Now, let's look at the Parthenon that I had explained earlier. Now, this building in Athens, built in 447 BC, is an example of the use of golden ratio in architecture. If you closely have a look at its dimensions, at the width, at the length, and if you also have a look at the height, the ratio from the bottom to slightly next to the top, as it goes to the top and to the roofing, will reveal a pattern that is inspired by the golden ratio.
And here we have the Vitruvian Man. Leonardo da Vinci used the golden ratio in a lot of his paintings and sketchings that he made and musings. And the Vitruvian Man is divided with the golden ratio. So from the soles of his feet to his navel, and from the distance from his navel to the top of his head, is the golden ratio. You'll find he's used it in other proportions, parts of the body as well, the arms, the legs, the face.
And here you've got Leonardo da Vinci's picture of the Last Supper. He was a scientist as well as an artist, and very, very interested in everything to do with engineering and science. And here he planned this picture of the Last Supper and the position of Christ there. And the lines show you how it the canvas was divided into sections, giving you the golden ratio. It's not necessary to go into detail about that, but it does show that he, Leonardo da Vinci, deliberately incorporated those dimensions in his picture there, the Last Supper.
Actually, every time I look at the Last Supper by Leonardo, it inspires how I usually take photos. I carefully look at the position of the main person or the main object in the photo. Now, if we look at Salvador Dali Last Supper, which was done in 1955, this particular painting reveals a great work that contains golden ratio in two ways. First, it is by the positioning, and second, if you look closely at the background, it harmoniously reveals a decahedron that is dominating the background of the image, which shows like a golden ratio that is occurring in many ways in regular pentagons and in regular dodecahedra.
So 300 years before Leonardo da Vinci, we are naming this ratio after a man also called Leonardo of Pisa, Leonardo Fibonacci. And so he was around 300 years before Leonardo da Vinci, and he was a son of a merchant. He was very well traveled and fascinated by doing arithmetic, methods of doing arithmetic. He wrote a book called Liber Abaci, the book of abacus, the book of calculation, and through that he brought the Hindu Arabic numerals into Europe and revolutionized how the European people did mathematical calculations. And the golden ratio, the Fibonacci sequence, is named after this man. And in his book, he wrote about the golden ratio. And
it's fascinating, isn't it, how the scholars learnt from the merchants. It was when Fibonacci saw how the Hindus, the Arabs, when he went along the Silk Road, how they did the calculations, he thought, oh, that's much better than the way the people in Europe do calculations. And he brought that knowledge into Europe. Now, one of the things he did was to give us this problem. And it's an interesting little problem. It's a sort of idealized family of rabbits. And so we've got to suppose, as Fibonacci did, that a newly born pair of rabbits, just one male and one female, they can mate at the age of 1 month. And at the end of its second month, the females mature and can produce another pair of rabbits. So supposing that happened, okay, supposing our rabbits have long lives and that the female always produces one new pair, one male and one female, every month from the second month on. And the question is, how many rabbits will there be at the end of 3 months? And how many at the end of a year? So let's just think a bit more about that. So what we have got, we're going to show our newborns in a sort of orange-coloured yellow spot, okay? We're going to show our 1-month-old young pair in pink. And then at the end of the second month, they become mature, and then they're shown in red. So if we go to the top here we have got our original pair, time t equals 0. So at the start, we've just got one newborn pair in yellow. And then after a month, we've only got that same pair, and they're pink, but now they're having fun. They're able to mate. And at the end of 2 months, lo and behold, you've got our pair that are now mature at 2 months, t equals 2, but across here, can you see the cursor? There's their baby, their pair of babies, actually. They're newborns, okay? And so let's show what happened at the time t equals 0. The original pair of newborn rabbits are shown the yellow disc. Time t equals 1 month, the same pair is shown in pink. At time t equals 2 months, the diagram shows the same rabbits, but they're now mature in red, together with a pair of newborns. We're up to time t equals 2. And then what happens at time t equals 3, our mature pair produce another pair of newborns in yellow, but our newborns from the previous month are now 1 month old, so they're shown in pink. So there are only the 3 pairs at time t equals 3, but at time t equals 4, oh my goodness, now there's some more. So at time t equals 4, we've got our original pair in red. We've got a newborn, because every month they have another pair of babies. Now our newborns in at the end of the 3rd month are now 1 month old, shown in pink. And our newborns who were born at the end of the 2nd month are now mature and are red, and they've produced a new pair. So now we've got 1, 2, 3, 4, 5 rabbits. And so we go on. So let's look at the writing. At time t equals 3 months, the original pair have produced a 2nd pair of newborns in orange, and their first offspring are now a young pair shown in pink. And the population is also shown at time t equals 4 and 5 months. And what we're asking you to do is to look at this tree diagram, perhaps draw time t equals 6 and 7 for yourself, and then to fill in the table. Now, in the table, you're going to, for the top line, you're only going to count the newborns, and for the second row, you're going to count the young pairs who are shown in pink, and for the 3rd row, you're going to count the number of mature rabbits, and the bottom row, you're going to add those up. So how many rabbits have you got altogether? So if we look at time t equals 5, we've got 1, 2, 3, 4, 5, 6, 7, 8 rabbits altogether. We've got 3 reds, so that's 3 matures. We've got 1, 2 pinks, 2 young pairs, and 1, 2, 3 sets of newborns. So you can fill in the table. So now we're going to pause and go and do that activity if you want to. And before you come back, switch it on again and we'll reveal the answers here. Now here they are, the tables filled in. We're going to ask you then conditions of what's been happening are described again at the top, and we're going to ask you what you see about the table. What we have got in the bottom row here is 1, 1, 2, 3, 5, and it goes up to 233, but you'll see 5, 8, 13, 21, 34. Oh, we've seen that before, haven't we?
This looks very familiar.
That's the Fibonacci sequence, we call it. And as Sam told us, each term is the sum of the previous 2 terms. So the formula or rule for getting each term is to add the preceding. So you add 8 and 13 to get 21. You add 13 and 21 to get 34. 21 and 34 added together give you 55, and so on. So that's our Fibonacci rabbits. And again, it's something that your learners could do they get this sequence, but also nice to do it in a group so they can check each other's work and explain it to each other. A group of, well, just a pair or 3 or 4 students together. It's a good number to work on this activity.
Now, remember the golden rectangle that I had shown you earlier, and I promised that we will solve together the ratio of the longest, the longer side, and the ratio of the shorter side. That gave us x over 1 to be equal to 1 over x minus 1. Now, if we cross multiply this, we will have x squared to be minus x minus 1 to be equal to 0, which gives us a very interesting equation called quadratic equation. Now, if we solve this equation, we will be able to find the value of x. Now, this value of x that we solve by using the quadratic formula is giving us 2 solutions. One of the solutions, is positive, which is the golden ratio that we found earlier, which is denoted by the Greek letter as O and a slash in the middle, which is equal to a figure of 1.618 given in 4 significant figures.
Now that Greek letter is called phi.
Now, Euclid in his Elements introduced the idea of the golden ratio, and as we see the picture of the Parthenon again, he what he studied and wrote about was the extreme ratio, which is the long AB to AC, which is, say, if that's the same as the mean ratio, which is AC to CB, then you're going to get the same, as Sam has just given us, the same equation out of that, the same ratio. X over 1 is 1 over x minus 1. And a question there in green, do you recognize this equation? So it was just thought about in a slightly different way by Euclid, but it is there, and that's how it was, the ideas were expressed in the design of the Parthenon. And again, as Sam just told us, the solution, the exact value is 1 plus root 5 over 2, which is just a bit more than 1.618. So when we come to the pentagon, which we've mentioned earlier, it's full of this golden ratio. So if we measure the lengths of the chords and the lengths of the edges, for example, if we test this by measuring AC, which is the chord length, and I've shown it in red here, and we measure AB, which is the edge length, AB, which is shown in blue, AB, and we divide AC by AB. Caroline, are you going to do that for us? She's shown us the picture there.
Yes, I'm just going to spotlight.
Oh, it's very nice and clear, Caroline. So would you like to measure, to do those 2 measurements?
So I've got 12.5 centimeters along the chord.
Caroline, I'm putting that into my calculator, 12.5, and that edge length.
The edge length is 7.8 centimeters.
Okay, and dividing one by the other, we've got 1.6. Not exact here, but it is very, very close, 1.602. Not 1.618, but very close. And if we go on to the next, all these pictures here, We're not going to stop and do this now and talk about the results, but you'll see that there's a lot your learners can do here in spotting the similar triangles that this is the pentagon with the pentagram, the star inside, and you'll see that there are some similar triangles there. And you can look at the angles there. So if you walk all the way round, you take 5 turns at the corners, and they must outside the shape, and they must add up to 360. So 360 divided by 5 is 72. So the external angle is 72 and the internal angle is 108. And you can ask your learners to find those angles and to list the triangles, and I've numbered them 1 to 10, and group them into sets of congruent triangles and spot all the similar triangles and work out all the angles. Lots of activities there involving our pentagon with a pentagram inside it, and each time you measure, you can measure the line in blue in this second one and divide it by the chord length, which I've now put in red, divide the red by the blue, and that's the golden ratio. In these triangles, the edge length, these isosceles triangles here, the edge lengths are in the golden ratio. In this triangle that you see, if you can see my cursor on the right-hand side here, the edge lengths are in the golden ratio. So we promised you that there was lots about the golden ratio in our pentagon, and they see it. Caroline's going to do a construction here, so I'll briefly tell you how she's going to do it, and then then Caroline's going to focus on and spotlight the visualizer so you'll see it better. So you take a square of paper, and what you want to do here is to fold it in half. So just fold it, or to bisect the base. You draw the diagonal. You can see this diagonal here, and it's got sides 1 unit and a half a unit, and then the other edge is √5/2 if you use Pythagoras' theorem. Now we've brought in the √5. You're going to draw BE as an arc, like we did for the elephant dreaming, with the center at M and radius MB. Draw that arc, and that will produce the golden ratio AFED. So Caroline is going to show us that.
First thing, we're going to create the recommended size is 10 centimeters. So we're going to use the top left-hand corner, another of those practical little tips before you start. I'm going to use...
You need to make a square, Caroline.
Yes, I'm making a square. So we're going to make a 10 centimeter square, and I'm just going to do in this instance by measuring. So I'm going to do 10, 10, going the other way, 10 and 10. There are other ways of doing it, but this is a nice replicable method that your learners can use easily in class. So I'm going to extend this base line because you will see we will want, so we're making a rectangle, not a square. We know that to start off with. So there we have a 10 centimeter square. Now what do I do?
Now you bisect the base.
Bisect the base. I can do that simply by folding. Super simple.
We could measure 5 and 5.
I could measure 5 and 5. I could have used my ruler and made a mark there, 5 and 5.
Now, you might like to just write the letters A at the top left hand, and then B on that square, A, B, C, D, A, B, C, D, okay? And the midpoint of the base is M. Now you draw the line MB now.
So I'm doing a diagonal from the base at M to the top right-hand corner at B.
Okay. Now that diagonal has length √5/2, and you find that won't start to fuss about it anymore, but because the edge lengths are 1 unit for the square, and you've got one BC is 1 unit and MC is a ½ unit. If you use Pythagoras' theorem, you'll find the diagonal is √5/2. Now, yes, okay. Now you want that length, so you're going to use your compasses and draw, or you're going to use your ruler, are you?
No, I found this lovely compass, found it
Okay,
at conference. So I'm going to actually use it, because I found when I was doing compasses with the other session that we did, you couldn't actually see what I was doing very well. So
okay,
just go
lovely.
through
So
this.
she's drawing an arc with center at M and radius MB, and she's going to draw that arc to find the point where it crosses the baseline. Oh, she's done it now, and that is E. Okay. Now then, if you draw a line perpendicular to that baseline, and that will make an edge of the rectangle there.
So as you can see, this is great for, again, like the elephant, for the learners to use the drawing equipment and have a bit of fun doing it, and do it in a real exercise, not in. So I've used a compass, a ruler, and a set square.
Fine. Now the rectangle ADE, top right hand, you can label that F. ADEF is a golden rectangle, and what you've got there is the square MEF, and well, we haven't got to put a letter at the top. N, call it N, say. You've got a square and a rectangle beside it, and that is what you've drawn is a golden rectangle. So as ME is √5/2, you have got AFED, the edges are 1 plus √5/2 for the long edge, or 10, multiply that by 10 actually, because
Yeah, this is 10 centimeters.
yes, but if you take that as your unit, you've got your golden ratio there.
Right. So
And
this, we'll call it 1 unit.
yes, that's right. And the other's 1 plus √5/2. Okay, well, that's really nice. We're going to do exactly the same thing again, but this time by paper folding. So if you look at this, you'll see the lettering is the same as what Caroline did, but instead of using instruments, you can do it entirely by folding. So you can actually hold this one up and show us as you do it, Caroline.
Okay, all right. Well, let me just start by measuring 10 centimeters. So I'm doing that. So I've got that first 10 centimeter measurement there. Right. I think I've got it in the right place. Yes, I do. I'm going to now.
And okay, so that's to make AD
Okay.
was 10 centimeters. Now, will you fold that corner A down to meet the baseline? And
I think to do this, I do actually need a line across, Tony. Because I can just fold it. Hello, right?
yes,
I
you
got
can do
it.
it by folding. And
I'm
do it all by
folding. Yes, thank you. I'm folding the whole. I'm just doing this flat on a table because so that I've got some level of accuracy here. And I'll show you what I've done. So what I've done is I've folded it nice and carefully so that so that's my guide. My 10 centimeter mark is my guide. And I folded it so that those two edges match, so that this is a 90-degree angle there. Right. So I now have, now I now fold this down to a square.
Yes, that's right.
Okay, folding that down to a square.
And now what you want to do is to fold it. Can you see the slide, Caroline?
I can see the slide.
Yes, and you
so-
fold AD, which is the edge, and you fold that to BC.
Okay. So to halve it basically.
Yes,
So
to
I've
find
got-
the midpoint M there.
right. So I've now folded that across. I did the original fold there, which has made my square, and now I've folded that across to the end of the square. So now I've got this fold here is the midpoint. So this is now M.
Right.
Okay.
And then number 4 here is you fold along BM, putting A at the back. So you
Right.
tap
Let me label it. So I've got A, D, that's B, that'll be C when it comes out, and I won't mark E and F yet. So I'm now going to fold along B, which is here. BM. So I'm going to make a fold that
and put
goes
A at the back.
through B and M.
And you're doing that because BM, as we saw before, was the radius of that arc.
Yes. Okay. So I've got,
And so now
I've
you
done that. So now I've got B, a diagonal fold that goes through B and M,
and put A at the back.
and put A at the back. So fold that down.
Yes.
So
So
now-
now where
okay.
your fingers are holding it, they're near that top point. Now what you've got is that is the radius, and you used compasses before, but now you can put that point down to from B down to the baseline, so that you will find the point E. So if you fold that edge, that folded edge, keeping A at the back out of the way, and fold B down to the baseline that you drew, you'll find the point E there.
And do I do it fold it along the base?
Well, B should actually lie on top of E, on the top of the base, and the point where it hits the base will be the point E. You found E.
So what I've done is so that's B, and I've folded it down where BM follows the base. So I'm folding that directly, so it lies on the baseline, and now B is now sitting on the baseline, and that point there is my new point E.
And that E is one of the corners of our golden rectangle.
Right, so let me mark that. Do I have to mark it, or am I going to?
Well, yes, you need to mark it.
Well, should I fold it? But if I'm only doing folding, let me fold it at that point.
Well, you can fold it so that the top edge goes back on itself to find the point F and complete the rectangle.
Yes. So there
So
we go.
with 6 folds, you find the golden rectangle AFED.
So I've now, the only thing is I've got to complete the F fold. So I've now folded, let me just mark them on. I've now folded, let me just repeat that again. I folded that down to find the point E, and then folded that across like that to find the point F.
Now, that's wonderful, Caroline. So if you smooth it out, Caroline.
Yeah, I'm just going to label it.
And you fold the square bits to the back, but smooth it out, you will find so that you have got the rectangle AFED. You should be able to hold it up and show us. And just sort of smooth it a bit. And
Get
then
my iron out.
you've actually produced the golden rectangle just by folding.
And I've done it on golden paper, just like you did. Hold on 1 second. I've folded it all down.
There you
And
go.
now we have
A golden rectangle. Okay, lovely.
Great. Now, as we move on, let us have a look at this. What do you notice in this formula? So the formula, if you can remember earlier, while we were solving the ratio between the longer side and the shorter side, and we ended up with a quadratic equation, we ignored the negative value and solved the used the positive one. But now if we have a look at this is x equal to a square root of 1 plus into square root of 1, and it goes on and on. And this, you might solve it like we solved the previous one and think that we are done there, because it will just give us 1.68 in 3 significant figures. But now, if we closely have a look at this, you will realize that we are not yet done. In the one that we solved earlier and got the solution to be 1.618 in 4 significant figures, but we are not yet done. Because if you closely have a look at it, this is called a nested equation, which is mostly common in high school, and you can do with your students. So if you have a look at this, the value of x is given by this formula that is equal to the golden ratio. In this case, phi is equal to the square root of 1 into a square root of 1 into a square root of 1, which sort of continues and gives us the golden ratio. How interesting.
I think it's a beautiful formula. And here's another one, and this is what we call a continued fraction. Now, what happens here, it's continued by 1 plus 1 over something, and the something is the previous continued fraction. So as you see it here, we repeat the pattern where x was replaced by 1 plus 1 over x. So just as in the last one, which Sam talked about, we got this root 1, and then we went on forever with the root 1s going in the next stage and another root 1. We've got 1 plus 1 over x. Now, what we do from the second to the third stage is the denominator at the third stage is the whole bang lot of the continued fraction at the second stage, and then we continue that, and it's an infinite process. So suppose we choose a value of x and calculate the values of these fractions, and we do this for x equals 2. 1 plus 1 over 2 is 3 over 2, and so we're going to put that into the second fraction and have the 3 over 2 in the denominator of the second fraction, which is 1 plus 2, which gives us the same as 1 plus 1 over 3 halves is the same as 1 plus 2 thirds, which is 5 thirds. So it's 5 thirds that we put into the third fraction, and the reciprocal of 5 thirds is 3/5, and 1 plus 3/5 is 8/5. And if we do that at the next stage, we've got 1 plus the reciprocal of 8/5, which is 1 plus 5/8, which is 13 over 8. And if you notice these fractions, they look very much like the ratio of the successive terms of the Fibonacci sequence. So what do we notice? Well, I've just mentioned it. And as you see what's happening here explained again with using an oval shape and showing how the previous whole continued fraction goes into replace the denominator in the next one, and we go on 5 thirds, 8/5, 13 over 8, and so on. And if you carry that on, it converges to, yes, you've seen it, you know about it. It converges to the golden ratio again. So now we come to a summary of all we have done, And my goodness, isn't that a lot of mathematics? And the GMSL in October 2022 was all about, that's our global maths lesson, was all about the golden ratio, and that's why it's at the top there. But what would you like to comment on something in this summary? What struck you? What would you like to comment on, Sam?
Now, as we summarize, going to have a look again at what I had mentioned earlier. When you are taking a picture, what usually comes to your mind first? For example, if you have a specific object that you want to be the center of attraction, does this idea of how Leonardo used the Fibonacci sequence to be able to come out with a very interesting drawing come to your mind? Or just how the picture of the Last Supper that is shown on the right-hand side looks like? Have a close look at it and assume that it was a picture and you are in the Last Supper and you are taking the Last Supper. Not overtaken by everything that is going on, but you also want to capture this moment in a picture. Would you consider the golden ratio? Now that is a beauty of mathematics that is in arts.
What was your favourite activity of all of these, Caroline?
Well, I love the elephant dreaming. I love the Fibonacci spiral, which you're constantly seeing in nature every time I see it, and the observing the Fibonacci sequence in nature. But for the activities, I just love the paper folding. I really love the fact that you can make all of this. We've got the this is not a perfect pentagon, but this is pretty close to it's not super accurate because it's folded, but it's very close to the golden ratio. And the two of them are so tactile and, again, memorable, as Sam said, that and you can then do all the ratios on this little rectangle, on this little pentagon. All of these activities are memorable. I just love the really hands-on.
Well, I rather like these formulae. The one that Sam talked about as the square root of, and under that square root, a whole infinite sequence of square roots of 1 plus the square root of 1 plus the square root. I like the way that just flows and we imagine it going on forever. And what value does it have? It has this value of the golden ratio. And the thing up at the top there, another beautiful expression, or sequence rather, where you can see the same repeating pattern and it converges to the golden ratio again. And then you wonder, don't you, about that pyramid. Could it have been chance that those ratios occurred in the pyramid? It seems unlikely that it happened just by chance. I think it was very clear that with the Parthenon, that definitely was built in and designed. With the Great Pyramid, it could have been chance, but I just think it was design. I think those people really did know a lot of mathematics. Okay, well, we hope that you will find a lot of use for these different activities with your learners. Certainly something where they can investigate and come up with these answers by themselves. So here on the Aiming High website, there's links for you to all these activities, and another one which we haven't done, which is 1 step, 2 steps, which you might like to try. There's a YouTube video there that you might like to look at as well. No, 2 YouTube videos. So we do recommend those.
Every day an activity gets posted on our Facebook page, which is something that you can just refer to or go through all of them and look for activities for you to do in your classroom.
And it's time to say goodbye, and we hope you've enjoyed this, and thank you for watching. Please use these. Let us know if you do, but it'd be very good that if you use these ideas with your learners, and try and help your learners to have a yes, I can attitude to mathematics.
And thank you very much, Sam, for joining us.
Thank you so much. And just my parting shot, when you are planning for your lesson and you are trying to make sure that your learners' previous knowledge or the knowledge they are coming with in class is conflicting with the learning goals that you have, how do you make sure that this kind of resource is useful for you so that you can be able to bridge that gap as close as possible? Thank you.
Thank you everybody for attending, and watch all our other videos.
This is a Global Teacher Empowerment Network video collaborating with AIMSEC and the Aiming High website. Our mission is to benefit children in disadvantaged communities all over the world by empowering the teachers who teach them mathematics.